Hello, everyone. Welcome to PMTTT's session 64. This is a special session, not just because this is the last session of the year. I hope everyone had a really nice semester and end of the semester. And it is a special session because we are hosting a young scientist from Saudi Arabia InterPore chapter, who are all from King Abdullah University of Science and Technology. So in this talk, I am joined here with Muhammad to help me. So without further ado, I can go ahead and introduce our first speaker, who is Xinyu Yao. She is a PhD candidate in KAUST in Earth Sciences and Engineering Department. And in today's talk, she'll be talking about interfacial properties of the hydrogen plus brine system in the presence of hydrophilic silica. Xinyu, the floor is yours.
Okay, thank you. Good afternoon, everyone. Today, I would like to present my research titled Interfacial Properties of the Hydrogen-brine System in the Presence of the Hydrophilic Silica. Background always goes first. Hydrogen is currently considered the second most important energy source after fossil fuels. As a clean, non-polluting energy, hydrogen has the potential to revolutionize global energy systems. It can be used for energy storage, electricity generation, and even in transportation without causing environmental harm. The effective development of a hydrogen economy offers huge benefits in terms of energy security, environmental sustainability, and economic growth. However, for this to be realized, hydrogen must be stored efficiently and cost effectively. A sustainable carbon-free hydrogen energy system is key to achieving this goal. It can be integrated renewable energy source like solar and wind. As shown in the figure, such a system combines renewable hydrogen production, storage, and supply into a unified framework. One of the main hurdles in the practical realization of a hydrogen economy is the safe and the effective storage of hydrogen, especially given its compressibility and volatility. Underground hydro Underground hydrogen storage (UHS) means hydrogen is stored in the geological reservoirs, has gained attention as a promising solution. The feasibility of this approach depends on a deep understanding of the geomechanical and geochemical behavior of storage state. Suitable storage locations include salt caverns and depleted hydrocarbon reservoirs. For underground hydrogen storage, wettability is considered one of the main parameters in evaluating the possibility of UHS. The interfacial tension and the contact angle between the reservoir lithology and the fluid naturally affect the residual fluid and surface wettability. These two properties directly affect the amount of gas that can be reserved and later recovered from the reservoir. So what are FT and wettability? Interfacial tension is a property of the interface between two immiscible phases. It is the free energy per unit area of interface at fixed temperature and pressure. FT occurs because a molecule near an interface has different molecular interaction than an equivalent molecule within the bulk fluid. Higher FT enhances the capillary forces and can hamper hydrogen penetration into reservoir rock, affecting the storage capacity. The wettability describes a fluid's ability to adhere to salt surface while in the presence of other immiscible fluids, defined by the contact angle at their interface. The wettability of hydrogen to rock is critical because it governs the maximum of hydrogen storage capacity, capillary pressure, injectivity, containment security, hydrogen saturation, residue hydrogen saturation. Therefore, wettability and interfacial tension must be accurately obtained. Recent studies have engaged in experiments to measure IFT and contact angle. However, this measurement can be challenging under sedimentary conditions, especially in extremely high temperature, pressure condition, or with toxic materials. This will lead to diversity in reported data. To address these challenges, molecular dynamic simulation provide a more accurate method for measuring them at different temperature, pressure, and also different ion types. So goes to the second part, simulation method. First, let me briefly introduce molecular dynamic. Molecular dynamics is a computer simulation method for analyzing the physical movement of atoms and molecules. The atoms and molecules are allowed to interact for a fixed period of time, giving a view of the dynamic evolution of the system. In the most common version, the trajectory of atoms and molecules are calculated by solving Newton's equation of motion. The forces and the potential energies often calculated using interatomic properties or molecular force field. MD can be conducted under different examples, including NVE, NVT, and NPT. In NVE examples, moles N, volume V, and energy E are fixed. And in NVT, the atom amount of substance N, volume V, and temperature T are fixed. And in NPT, the moles N, pressure, and temperature are fixed. We can think of MD as a visual experiment. During simulation, these equations supply the potential energy models for band stretching, angle bending, dihedral torsion, and the non-banded interactions. For the non-banded interactions, two-part, Lorentz-Jones and Coulombic terms. So for MD simulation, it is critical to build a suitable MD simulation, MD model, and choose an appropriate force field. In this research, I developed two models, a model of a brine hydrogen system to calculate the interfacial tension, and another model presenting hydrogen-brine silica system, where brine droplets are sited on the center of the silica surface and surrounded by hydrogen. On the top of the hydrogen with a piston applied to maintain constant pressure. For the first system, the NPT equilibrium run for 6 nanoseconds and then 4 nanosecond NVT production run. I computed 4 independent simulations to achieve good statistical averages. For this 3-phase system, first I run 8 nanosecond NPT equivalence and then 4 nanosecond NPT production run. I also compute 3 independent simulations to achieve good statistical average. After obtaining the molecular trajectory through simulation, calculating IFT and contact angle requires additional steps. For interfacial tension, it was calculated directly from the principal components of the MD simulation self-stress tensor using this equation. And for the wettability, first the density distribution is calculated under grid. We defined the fluid-fluid interface as the isodensity profile with a density equal to 0.5 is the half of the droplet bulk density. The isodensity profile is composed of isodensity point along the interface, the black point in the finger. Then use circle to fit those isodensity points and get the contact angle. Next is the force field selection. For brine, we select the TIP4P 2005 force field to represent water molecules. This choice is driven by its better performance in predicting surface tension. To simulate the influence of ion types, we include sodium chloride, calcium chloride, and potassium chloride here. The surface tension calculated using this force field for the brine match well with the experimental data. Detailed parameters are summarized in the table. For hydrogen, we select a newly developed rigid force field optimized for small gas molecules. And the detailed force field parameters are also provided in the table. To validate the force field, we calculated the density and the surface tension of brine using the selected force field and compare the result with experimental data and other simulation data. For silica, the validation involved analyzing the contact angle of brine on silica surfaces. This result shows a strong agreement between simulation output and experimental data. This confirms that the selected model and the force field parameters can effectively represent the interface properties of brine and gas system. Now let's discuss the simulation result obtained from our analysis. First, for the hydrogen-brine system, I calculated the interfacial tension and found that the interfacial tension increases with salt molality for all sodium chloride, calcium chloride, and potassium chloride. Notably, the interfacial tension for calcium chloride is especially sensitive to changes in salt concentration. I also analyzed the density profile of the two-phase system. The hydrogen density profile remained relatively constant across different brine types, while the water density profile showed significantly variation in water-rich region. Unlike CO2 or nitrogen, hydrogen molecules did not accumulate at the interface. To provide a clear comparison, I measured the phase density of both brine and the hydrogen phase. With increasing salt molality, the water density increased, while the hydrogen phase density remained unchanged. Water phase density is larger and under higher pressure and lower temperature. Furthermore, I evaluated the hydrogen solubility in a brine phase. The result indicated that hydrogen solubility decreases with the increase of salt molality, and the solubility is more sensitive to the molality under higher pressure. For the contact angle simulation, I found that the contact angle for sodium, calcium, and potassium chloride droplet rises with increasing salt molality. Higher temperature and pressure also result in larger contact angle for brine. Finally, I got the equilibrium distribution of brine and hydrogen normal to the silica surface from MD simulation in the region of the brine droplet and in the hydrogen-rich region. The black area in the fingers. From the fingers, it shows two water adsorption layers in the central region of the droplet. And in hydrogen-rich region, there shows a adsorption layer of water and hydrogen near the silica surface. Last is the summary. In this In this study, molecular dynamic simulation were conducted to predict the interfacial properties, interfacial tension, and the contact angle for the system of hydrogen-brine at different pressure, temperature, and ion concentrations. The key findings include interfacial tension of sodium chloride, calcium chloride, and potassium chloride hydrogen increases with the increase of salt molality, and the interfacial tension of calcium chloride hydrogen is most sensitive to salt concentration changes. Contact angle of brine increases with the increase of salt molality, and the contact angle are larger at higher temperature and higher pressure. I hope this insight contributes to optimizing UHS for a sustainable hydrogen economy. Finally, I would like to thank my advisor, Professor Shu Yu-san, co-advisor Professor Bi-Chen Yan, and Dr. Irene for their guidance. Special thanks to computational resources of the Shaheen 3 supercomputer by the KAUST. And that's it. Thank you for your attention. Welcome any questions.
All right, thank you, Xinyu, for the very nice presentation. It was really surprising to me to see how your computation results aligns well with the experimental results. We can now take any questions for Xinyu. I think we already have one question that came up from the virtual audience. So it's from Mehdi. So the question was, how did the authors consider the impact of factors like line tension for contact angle prediction?
The interfacial tension will affect the contact angle, but the contact angle not only affected by the interfacial tension, it can also choose other silica surface. If we choose other silica, it will be like oil wet surface. It will be very different result.
Okay. We had another question from Yichun Wan. The question is, what is the size of the model? Will it affect the simulation results if the model is too small?
The size of our model is very small. It's only about 2 nanometer. But simulating a small system will affect the result. To solve this problem, we often use periodic boundary conditions. We confine the system in a box and assume the properties of the actual system can be approximated by a virtual infinite system of repeating side by side box. If the molecule passes through the box boundary, it will re-entry the box from the opposite boundary. This is a boundary periodic boundary condition.
I see. I had a number of questions for myself. Maybe I missed it. Did you model the water molecules, individual water molecules, or did you model the water as the continuum?
The water molecules. Here, I consider the salt molality. So this one, for 0, it is pure water. Mm-hmm. So for all the simulation, we simulate the pure water, and then add different ions and different salt concentration.
I see. And my another question is, you mentioned in the intro that typically hydrogen gas is injected into depleted hydrocarbon reservoir. So would the presence of previous hydrocarbon impact the hydrogen injection and its saturation? How would that impact the saturation?
It will impact, but I didn't consider here. I'm doing this, consider the like mass CH4 or CO2 or nitrogen, the effect of this gas to hydrogen storage.
I see. Okay, I don't think we have more questions from the virtual audience. And with this, I think we can conclude our first session. Thank you, Xinyu.
Thank you.
Yeah. And Mohammad, please.
Yes, excellent. Thank you very much for your excellent talk and for sharing your interesting results with us. Now it's time to move on to our second speaker. Our second speaker is Ronghao Cui. He is a PhD student in Earth Science and Engineering at King Abdullah University of Science and Technology, or KAUST, in Saudi Arabia. His expertise lies in numerical simulation for fluid thermodynamics across different scales, which is mostly focused on molecular simulations and Pore-network modeling. Thank you, Ronghao, for joining us today, and the floor is yours.
Okay, thank you, Mohammed and Sound, for hosting our presentation. Hello, everyone. My name is Ronghao. I'm from KAUST. So today I would like to talk about something related to thermodynamic effect of multi-component two-phase fluids in porous medium. Actually, we finished this work by Pore-network modeling in collaboration with Professor Xinyu Yao and Professor Majid Hassanizadeh. So, well, first of all, please allow me to introduce a little bit industrial applications about fluid thermodynamics. I have to say for fluid thermodynamic properties is very important in subsurface engineering, particularly for current gas geological storage and also the enhanced oil recovery. Those physical processes always involve a very complicated phase transition and phase interactions among multiple phases in the subsurface. So for porous medium, we are quite interested those phase interactions could have what kind of effect on the porous medium. So for porous medium, and we calculate the constitutive relationship by Pore-network modeling and see what happened in this work. So, well, so speak of Pore-network modeling. So actually, such a numerical tool can simplify the natural porous medium into 3D disarrayed topology with simple geometries, including pore bodies and porous roots. So in Pore-network modeling, we will involve two different parameters. One is shape factor, and we can use this parameter to characterize the cross-sectional geometries for a circle, square, and a triangle. And we also need to use the shape factor to correlate the fluid conductivity in our simulation. Another parameter that is coordinate number, and which is defined as number of porous roots connected with a single pore body. And we can use the coordinate number to characterize the connectivity in a Pore-network model. So, well, I have to say for a Pore-network modeling, it has a wide range of applications, including fluid flooding, solute transport, and thermal transfers. And if we would like to use Pore-network model for the flow simulation, so at least we need the network structure. So there are two different ways. The first way is we can build a digital log and extract the Pore-network structure from the digital log. And I'm gonna present another way, that is we develop a network generator. So in this way, we can skip the process of the digital log and to match and our expectations. Here, so for the network generator, we need to predefine a four-connected topology. Here we use a multi-directional topology whose maximum coordinate number will be 26. And well, we can modify this four-connected topology into less connected topology by bond removal process. However, this process will causing some irregular components that we don't want, such as isolated nodes, dead nodes, or isolated clusters, and those irregular components will causing some numerical issues. So that's why we would like to get rid of them. I mean, for isolated nodes and dead nodes, it will be easier to get rid of because they have a specific coordinate numbers. But for the isolated clusters, it will be more challenging. So I'm going to show that how can we get rid of the isolated clusters. So we represent network as a graph. And if it is a graph, we have a lot of optional graph transversal algorithms that we can use to visit all nodes and identify the isolated clusters and then get rid of them. And by the way, we can also identify the isolated nodes and isolated clusters together and get rid of them because the graph transversal algorithm can do that. And so after confirming the network topology, we would like to move to pore morphology, including pore geometries and also the pore sizes. So here we use the cube as a pore body, and for pore root we use square cross section. And for pore body size, we use the base 10 log normal distribution, and we generate such a distribution by Box-Moller transformation. And we correlate pore root size to the pore body size, and which in this way we can determine the pore morphology. So and after that, then we can generate our 3D representation for our Pore-network model as we showed here. And with this Pore-network model, we can perform the structure property analysis. And we run 5 realizations with the same input to evaluate the error bars for the different structure property, including pore body radius, pore root radius, and coordinate number distributions. And well, that is our network structure model. And if we would like to simulate multi-phase flow in a Pore-network model under quasi-static condition, we also need the extended local saturation rule. And we developed this rule to which can accommodate a certain range of contact angle from 0 degree to 45 degree for pore bodies, and so that we can consider the wettability effect. And so after that, we perform the standard quasi-static modeling in Pore-network model to calculate several constitutive relationships in porous medium. So here, first we calculate capillary pressure curves. And we scale capillary pressure by interfacial tension as a function of liquid saturation. We can see that all of the scaled capillary pressure curve will collapse to the uniform curve. And of course, that if we change network structure, we can observe the scaled capillary pressure will change. But in this figure tells us that once we have scaled the capillary pressure curve, and we also know the interfacial tension, we can retrieve the original capillary pressure curve. And also for the original capillary pressure curve also remains sensitive to the contact angle, that is wettability effect. And if we go to interfacial area and saturation relationship, we can see that such a relationship is independent of the interfacial tension. But for wettability, it still have a very significant influence on such a relation. And so after that, we also perform the steady state flow simulation to calculate the relative permeability saturation relationship. And we can say that for interfacial tension, there is no influence on the relative permeability. So that is a standard quasi-static modeling to calculate constitutive relationships in the porous medium. And because we would like to explain the thermodynamic effect in the porous medium. So in this way, we extended the standard KAUST study modeling to include the fluid thermodynamics inside. So we mainly consider interfacial tension variations, and we use the contact angle as input. I'm gonna show how can we model this. So here we assume that the gas and liquid has a non-winding phase and a winding phase respectively, and we also need to create a phase equilibrium across the network, including mechanical equilibrium and chemical equilibrium. And well, for the network, it will be connected with gas and the liquid reservoir as its inlet and outlet size with a specific absolute pressure. Well, different from the standard KAUST static modeling, we assume that for the inlet and outlet reservoir, both of them have limited volume to accommodate certain components. So, which means for the fluid thermodynamic properties, will influence the values of interfacial tension and then vary the entry capillary pressure. So in this way, that is our model. And here is our computational procedure for our model. And first, because we involve hydrocarbons inside, so which means first we need to do the phase stability test to make sure there exist two phases. So if there are two phases, we can do the flash calculation and also involve the other local rules in Pore-network modeling to perform the gas drainage in the network model, and then we can calculate the different constitutive properties inside. So here, first we start the most simple system, that is a binary component system, which is composed of Mason and pentane. So here we use the phase stability test to calculate phase envelope, and then we can see for the interfacial tension as a function of fluid pressure curve. So in these curves, as long as we have the same temperature and same fluid pressure, no matter what composition it is, we can still have the same interfacial tension. So in this way, if we have a condition of the same temperature and the same capillary pressure, as long as we change the fluid pressure, we can still see the variations of saturation in the porous medium. So in this way, we would like to use capillary pressure, saturation, fluid pressure surfaces to explain the capillarity variations in the binary component system. However, it is not the case if we consider multi-component system. Here I just we selected two different systems. One is 3-component system, another one is a 4-component system. We also do the similar things to calculate phase envelopes and to calculate the interfacial tension. We can say that even if we have the same temperature and the same fluid pressure, as long as we have different composition in the system, we can get totally different interfacial tension. So, and we can still have the different fluid pressure saturation curve in porous medium. And I would like to use more intuitive way to highlight the capillarity complexity in the multi-component system. And we also calculate capillary pressure, saturation, and the fluid pressure surfaces in for these two component system. And we can say that as a different temperature and different compositions, we can have totally different surface geometries in such a component, in multi-component system. And well, in order to highlight the composition effect in the multi-component system, we use a 3-component system to investigate how composition effect it will be on the capillary behavior. So here we use stability test to calculate phase envelope as a function of mole fractions of 3 components. And well, we can see from the interfacial tension, even if we have the same temperature, same fluid pressure, as long as we have different composition. And by the way, in this system we have the same spaces in such a system, but we have different compositions. So we can, in this way, we can observe the different variations of interfacial tension. And so if we change the mole fractions, we can observe the exist very significant changes of the saturation, as we showed in this figure. So here I calculate the capillarity as a function of saturation and a mole fraction of decay as a different temperature and fluid pressure. You can see that there exists, even if we have the same temperature and fluid pressure, but we change the composition, we can still observe there exists a difference on the capillarity. So that is the capillarity in the multi-component system. And so that is all my talk. I would like to do the summary for my presentation. So first, we extended the standard quasi-static Pore-network modeling to include the fluid thermodynamic properties. And then, because for binary component system is a special case, so we can use the capillary pressure, saturation, fluid pressure surfaces to explain the variations of capillarity. But if we have 3 or more components, I mean, we would like to highlight the composition effect on capillarity because it will be very important and more complex. And because actually in our model, we use constant contact angle, but we have highlighted how interfacial tension can influence the capillarity. And the interfacial tension changes, it is because the compositional effect. So that is all my talk. I would like to acknowledge my professors, Professor Xinyu Yao and Professor Majid Hassanizadeh, to make this work happen. And I also would like to thank Dr. Ethan Lee and Dr. Sidian Chen for their valuable discussions. And thank you. If you have any question, I will be more than happy to answer that. Thank you.
Thank you very much, Ronghao. It was a very interesting research, and I'm guessing that the audience will appreciate what you presented here today. I have 2 questions of my own. The first one is about the PNM. When we use PNM, the computational cost is something that is attractive for us. What happens when we include the thermodynamic computations into PNM? How heavy it becomes, and how you handle the situations when you have multi-component in your system?
Yeah, actually, here we consider the 2 components, 3 component, and 4 component system. But for Pore-network modeling, actually, it will have less demanding on the computational resources. I have to say that because yes, it will be faster, and it also depends on what kind of size we can have. Actually, here I use 30,000 Pore bodies for the calculation, and it will be quite fast. But I mean, if we finish the whole procedure, including stability test and flash calculation and also the flow simulation, I mean, I believe that it will be faster than other direct numerical simulation, like lattice Boltzmann and also the computational fluid dynamic simulation. Yeah.
But can you give us some numbers about what is fast and what is slow, and how much does it cost in terms of computations?
Actually, because I didn't run our simulation by direct numerical simulation, but I have to say that because we are doing this on the quasi-static condition, so I'm sure that if we use direct numerical simulation, you have to make sure the flow simulation to reach the quasi-static modeling. But for this, I mean, we can just within 3 hours, we can finish all of the simulation on our own laptop. Yeah.
Interesting. Now we have one question from the audience. Hi, Ronghao. Many thanks for your insightful talk. My question is, if you include phase equilibrium calculations in your quasi-static Pore-network modeling, how can you consider capillary pressure? It's a question by Zhen Zhu.
Oh, thank you. I have to say it's a very good question because actually I can show that figure. I mean, for the binary system, because in this figure we include fluid pressure and also capillary pressure curve here. And we can see that compared with the capillary pressure, I mean, we have a much larger fluid pressure here. So Actually, for the phase equilibrium calculation, we didn't consider capillarity in specifically for the phase equilibrium calculation. But as I know that if we consider like a nanoporous medium, I mean the capillary pressure will be significant in the phase equilibrium calculation. So that in this way we need to consider that. Yeah, thank you.
Okay, very interesting. Just maybe it's going to be the last question of the session. How would you change your simulation framework if you want to include associating or polar molecules, or even if you want to go towards the ionic compounds? What will you change and how it will impact the entire framework?
Yeah, I think the most important thing is we need to use different equation of states. And because in our computational procedure, and the most important thing is we need to run the phase equilibrium calculation. And after determining because if we want to get more accurate interfacial tension, we need to use the appropriate equation of state. So here, because we are focusing on the hydrocarbon, though the general Penrobinson equation will be satisfying for our simulation. Yeah, thank you.
Excellent. Thank you very much. Thank you, Ronghao, again for your very interesting talk. Now we can wrap up the session. We will come back next year, 21st of January, and we will have a US-based session. We will invite Wei-Peng Yang from University of Minnesota. He will talk about fluid inertia that controls fluid mixing and mineral precipitation in fractured and porous medium. And we have Nathan Jones from Caltech, California Institute of Technology, and he will talk about pattern formation of freezing infiltration in porous medium. Please subscribe to our channel and so you get the notification when we will announce our upcoming sessions. With that, I would like to close the session. This is the current porous media TTIM talks. And if you are interested in presenting your research, please let us know. You can get in touch with us, and we will arrange a session in the coming months. With that, I would like to close the session and have a great day or great evening for all of you. Bye-bye.